Software design patterns, according to the classic definition by Gamma and his colleagues, are not finished segments of code. They are abstract templates that identify specific classes and their operational rules, completely independent of the programming language used. The central tension in object-oriented design is that building a highly reusable system demands flexible problem decomposition, yet standard methods of object creation inherently restrict that flexibility. Relying on the new keyword hard-codes the exact class you want to instantiate, forcing tight coupling between client code and the concrete implementation. Under external pressure or changing requirements, this tightly bound, hard-coded architecture creates a brittle system that breaks rather than adapts. To build scalable and reusable software, architects must abstract the entire object instantiation process away from the client code. The client should request an object without needing to know how it is built. Recognizing this instantiation bottleneck is the dividing line between simply writing functional code and actually architecting a resilient system. This 1995 Gang of Four classification matrix is our definitive map. Its vertical axis represents scope, distinguishing whether a pattern applies to classes via static inheritance or to objects via dynamic composition. The horizontal axis represents purpose, categorizing patterns into creational, structural, and behavioral domains. We focus strictly on the creational column, whose core goal is encapsulating which concrete classes the system uses, hiding how instances are created. By mastering these specific creational tools, an engineer gains the vocabulary required to resolve the exact coupling problems caused by hard-coded object instantiation. The baseline solution is the factory method. It simply defines an interface for creating an object, but delegates the actual instantiation to its subclasses. The architectural challenge escalates when a system needs to generate entire families of related or dependent objects while still refusing to specify their concrete classes to the client. The solution is the abstract factory pattern, sometimes called a kit. It operates one level higher than a standard factory by allowing a class to return an entire factory of classes. This UML diagram models a real-world analog, Japanese automobile stamping equipment. It demonstrates exactly how an abstract factory operates. The stamping equipment base class provides the overarching abstract interface for the manufacturing process. The inheritance path flows down to concrete factories. Each of these implements the interface to manufacture components for one specific model of car. These concrete factories handle the synchronized output of specific, related families of products. If the system calls for Model 1, the factory ensures the left doors, right fenders, and wheels produced all match that exact vehicle. The client triggers a highly complex, multi-part manufacturing process, but remains entirely decoupled from the concrete classes actually being produced on the assembly line. A different constraint emerges when an object's creation requires a complex algorithm and cannot be executed in a single, distinct step. This requires the builder pattern. Unlike the abstract factory, the builder's specific intent is to separate the step-by-step construction of a complex object from its final representation. We can observe this in a diagram mapping out a custom PC configuration system. The director class manages the timeline of the build. It issues specific sequential commands to the builder interface. Downstream, the concrete builder executes those commands. As it processes the requests for CPUs or RAM, it accumulates and stores the internal state of the complex object over time. In the final step, the client extracts the fully assembled, finished representation from the builder interface. The builder pattern provides immense structural flexibility. The exact same step-by-step construction process, dictated by the director, can be used to assemble wildly different internal representations of an end product. We must also account for extreme instantiation costs. In scenarios following heavy database operations or the loading of massive game assets, invoking the standard new keyword drains system resources. This structure outlines the prototype pattern, which bypasses standard instantiation entirely by copying an existing instance. The pattern relies on an abstract base class specifying a pure virtual clone method. When called, the concrete implementations directly duplicate their existing prototypical instances in memory, bypassing the resource tax of building an object from scratch. At the opposite extreme are systems that require strict lockdown of global state management. This is the domain of the singleton pattern. Its constraint is absolute. It ensures a class has only one instance and provides a singular global point of access to it. A log manager is a standard use case. It acts as a mandatory bottleneck, maintaining a hierarchical namespace of shared logging state for the entire system. This singular instance can be created at load time through early instantiation, or delayed until it is actively required via lazy instantiation. The prototype and singleton patterns solve opposing ends of the creation spectrum. One maximizes efficiency for heavy, repeatable objects, while the other strictly restricts access for vital global states. The driving logic behind all creational patterns is to permanently decouple the client from the concrete realities of how objects are instantiated. We progressed from simple factory methods delegating tasks to subclasses up to abstract factories outputting entire families and builders executing step-by-step assembly. We then secured the edge cases, utilizing memory cloning for efficiency and absolute restriction for global control. But while creational patterns elegantly solve how objects are born, they offer no guidance on how those objects live, interface, and interact with each other. Returning to the GoF matrix reveals the next architectural hurdle. The creational domain is mapped. The focus now shifts to the structural column. These patterns manage how individual objects and classes are combined to form much larger functional systems. The composite pattern, for instance, allows clients to treat a single leaf object and a massive part-whole hierarchy with exact uniformity. Understanding how entirely incompatible interfaces are bridged requires a dedicated analysis of this structural domain. Mastering object instantiation provides a solid foundation. True system architecture requires orchestrating those disparate instances into unified, resilient structures.